Tonight, we're going to explore one of the most revealing silences in the history of human achievement. On December 14, 1972, Eugene Cernan climbed the ladder of the Apollo 17 lunar module and lifted off from the surface of the moon. He was the last human being to stand on another world. More than 50 years later, he still is. When he left, the personal computer did not exist. The internet did not exist. The first cell phone call was a year away, and Voyager 1 had not launched. Every technological revolution since has happened while no one has travelled farther than low Earth orbit. The usual explanation is simple. Budget cuts, lost political will, a Cold War that ended. But the real reason is stranger than that, and more unsettling. The question was never about money. It was about something harder. What a civilization can begin, and what it fails to sustain. By the end of tonight, you're going to understand why Apollo was never truly about the moon, why the knowledge to return was allowed to vanish, and what that long silence reveals about the kind of civilization we are. Before we get started, take a second to like and subscribe if you enjoy these videos. It really helps a lot. Now let's begin. No one who has been born since that night has ever watched a fellow human being walk on anything but Earth. Sit with that fact for a moment, because the number alone does not do it justice. In December of 1972, the Vietnam War was still grinding on. Richard Nixon had just won re-election in a landslide. The World Trade Center had just been completed, its towers brand new against the skyline. Now, hold that image next to everything that came after. The personal computer arrived, then reinvented itself a dozen times over. The internet arrived, then rewired how the entire species communicates, works, and remembers. Cell phones went from a single phone call to a device in nearly every pocket on the planet. Voyager 1 launched, crossed the orbits of every outer planet, and kept going until it left the heliosphere altogether, the bubble of the sun's influence, and entered interstellar space. Every one of those revolutions happened underneath a sky that, for human beings, stopped changing the moment Cernan's boots left the ladder. Think about how strange that split actually is. Down here, almost nothing stayed the same for 50 years. Up there, almost nothing changed at all. A species that rewired its own civilization twice over could not manage to send a person back across 250,000 miles of empty space it had already crossed 9 times before. Here is the plain version of that fact. The entire digital age, the entire information age, the modern internet in your hand right now, all of it unfolded while no human being travelled farther from Earth than a few hundred miles up. Not to Mars, not back to the moon, nowhere. So the question is obvious. Why? And most people already carry an answer around without ever examining it. Budget cuts, lost political will, a Cold War that cooled down and took the funding with it. That answer is not false. It is just not the real one. It is the kind of answer that treats a symptom as though it were the disease. Budget cuts happened, yes. Political priorities shifted, yes. But naming those things does not explain why they happened, and it stops the inquiry exactly where the more revealing part of the story actually begins. But here's where it gets more unsettling than the standard version admits. Here is what a closer look at those 50 years reveals. The reasons Apollo ended are not simply facts about 1972 and 1973. They are facts about something much larger than one program or one decade. What a species chooses to value. How a civilization decides again and again to spend its largest and rarest resources. And most of all, what it actually takes to sustain the hardest thing that civilization has ever attempted, once the attempting stops being new. Not a footnote about one cancelled budget line. Not a single villain in a single Congress. A pattern repeated for 5 decades in how ambition gets built and how it gets allowed to fade. That last part is the real hinge, and it is worth naming clearly now, because everything that follows circles back to it. Beginning Apollo took extraordinary will. It took a nation deciding in public to do something that had never been done, on a schedule measured in years rather than decades. But sustaining that achievement, or building something equally ambitious in its place, turned out to demand something rarer. A civilization can prove once that it is capable of a singular, spectacular act, spending whatever it takes, moving whatever needs to move, for as long as the will holds. Whether it can keep choosing that act year after year, budget cycle after budget cycle, long after the moment that made it urgent has passed, is an entirely different test. Most civilizations, it turns out, never even get asked the first question. Fewer still survive the second. Apollo passed the first test so completely that 12 human footprints are sitting undisturbed in lunar dust at this exact moment. No wind to blow them away, no rain to wash them out, no weather at all to erode them, because the moon has no atmosphere to carry one. They are simply there, waiting, exactly as they were left, while an entire world changed underneath them. It is the second test, the sustaining, that has quietly failed for more than 50 years. This will not be a political argument, and it will not be a lament. It is an honest accounting of what happened, examined cause by cause, structure by structure, so that the shape of the failure becomes visible instead of assumed. Every reason that follows is drawn from the historical record, not from speculation about what anyone secretly intended. Not because that version is comfortable, because it is truer and stranger, and says something about us that the budget cut explanation was never built to say. To find that shape, start with what Apollo actually was, underneath the achievement everyone already knows, not the myth handed down in documentaries and anniversary specials. The machinery that made the myth possible in the first place. And that machinery is where the story actually begins. The machinery starts with a name most people already know, but not for the reason they think. Wernher von Braun stood at the center of the Apollo program as its technical director. The man whose calculations turned rocket dreams into liftoff. Look one step further back though, and the same name attaches to a very different building. At Peenemünde, on Germany's Baltic coast, during the Second World War, von Braun held the same job title, technical director, except the rockets he was directing then were not headed to the moon. They were headed to London. The equations that later put 3 men on lunar soil were close cousins of the equations that once carried a warhead across the English Channel. The mathematics barely changed. Only the target did. That is what it means to call Apollo a weapons program that landed on the moon, not as an insult aimed backward at anyone, but as an origin story. That is not a coincidence buried in a footnote. It is the shape of the whole story. Apollo gets remembered as a triumph of exploration, the fulfillment of an ancient human wish to leave the Earth and stand somewhere else. That description is not wrong. It is just not complete. Strip away the myth and a plainer sentence sits underneath it. Apollo was a weapons program that happened to land on the moon. Not a conspiracy, not a hidden agenda whispered in back rooms. A straightforward historical fact, traceable through public budget records and public engineering lineages, plain enough that no one ever had to hide it. The Saturn V, the rocket that carried 3 men to the moon and back 6 times, did not appear out of nowhere. It was the end point of a line that started with the German V2, the world's first long-range ballistic missile, continued through the intercontinental ballistic missiles the United States and the Soviet Union built through the 1950s, weapons designed to carry a warhead across an entire ocean, and only then turned towards space Once a political moment made that turn valuable. The engineers who built the Saturn V were the same engineers, or the direct students of the same engineers, who had spent their earlier careers building rockets aimed at cities. Not toward orbit, toward capitals on the other side of the planet. The factories, the fuel technology, the guidance systems, all of it built for two purposes at once, war and space alike, whichever purpose happened to be paying for it that decade. Built first for war, repurposed for the moon once the moon became useful. None of this is an accusation against the astronauts or against the engineers who poured their working lives into getting 3 men to another world and back alive. It is a statement about the context that made their achievement possible in the first place. A context built on missiles, not on wonder. The wonder was real, it just was not what paid the bills. Here is where the machinery shows up in the numbers themselves. The United States was locked in an existential contest with the Soviet Union, a competition where rockets served as a visible scoreboard for something much larger and much darker. A rivalry in which the same booster that could lift a capsule into orbit could just as easily lift a warhead onto a city. Because that competition was treated as a matter of national survival rather than a matter of curiosity, it pulled in a kind of funding peacetime science never receives on its own. Ask why a government at peace would pour money into rockets at wartime levels, and the honest answer is that it was never entirely at peace. In 1966, at the height of Apollo's development, NASA's budget reached close to 4.5% of the entire federal budget. Scaled to the size of today's federal budget, that same share would come to roughly $180 billion every year. Now, hold that number next to the one that actually describes NASA today. NASA's current budget sits at around $25 billion a year. $25 billion is a little less than 1/7 of $180 billion. Picture a household that once poured a full week's paycheck into its most ambitious project. Today, that same household spends less than a single day's wages on the very same kind of undertaking. Not a modest decline, a collapse in scale that rarely gets described in those terms. 180 billion a year against 25. That gap is the entire difference between a civilization racing to the moon and a civilization visiting it in memory. Only one destination in the solar system was close enough to reach on the timeline the rivalry demanded, visible enough for the whole world to watch, and dramatic enough to serve as final, undeniable proof of missile supremacy without a single shot fired. That destination was the moon. Not chosen for its geology, not chosen for its water or its dust or its mineral history, chosen because it was the biggest stage available for a competition that was really about something else entirely. Here is the reveal sitting underneath the myth, stated plainly. The money was never really about the moon. The money was about missiles, about a nation frightened enough of a rival to fund whatever a missile program asked for. The moon landing is what happens when that much money, that much missile technology, and one specific political moment all line up at the same time. Hold all 3 of those conditions in mind, because none of them is permanent by nature. Money tied to fear rises and falls with the fear itself. Technology built for one purpose can be redirected, but only while someone is still paying to keep the factories running. And a political moment, by definition, passes. Apollo needed all 3 at once, and for a few extraordinary years in the 1960s, it had them. Which raises a question the standard story never quite asks out loud. What happens once the money stops being about missiles? What happens once the political moment passes and the fear that funded it cools? That question would not stay hypothetical for long. The very thing that made Apollo possible, a fear-funded, missile-shaped, temporary alignment of politics and money, was never built to last. Its expiration date was closer than anyone standing on the moon in 1972 could have guessed. That expiration date arrived early, and it arrived quietly. Not as one dramatic announcement, but as a slow sequence of budget decisions spread across 5 years, each one small enough to pass without much notice on its own. The Soviet moon rocket had already failed test after test, so the rivalry that had justified the spending began to lose its edge. If the other side could not even reach the moon, racing them there stopped feeling urgent. Vietnam was absorbing political attention and political capital that space exploration once claimed. A war that grew more expensive and more divisive with every passing year. Cultural upheaval through the late 1960s, protests, assassinations, a country arguing with itself, was pulling national priorities away from a single, symbolic destination and toward problems closer to home. In 1967, the money for Apollo started disappearing. Not all at once. Year after year, appropriation after appropriation, through 1972, a 5-year bleed that most people watching the landings never noticed happening underneath them. Apollo had taken most of a decade to build. It took barely half that long to dismantle. The Saturn V production line closed in 1968. Sit with that for a moment. The rocket that would carry the last 3 Apollo missions to the moon in 1969, 1971, and 1972 had already stopped being manufactured before any of those flights happened. Finished rockets, machines capable of carrying human beings to another world, sat in storage buildings with no missions assigned to fly them, hardware waiting for a program that no longer existed to use it. 3 more landings, Apollo 18, 19, and 20, were cancelled between 1969 and 1970. Not because the moon had been fully explored. Not because the science was finished. Because the budget line had been cut and the political appetite for the moon, so recently insatiable, had simply run out. Here is the first structural cause, and it deserves to be said plainly. The program was cancelled before it was finished. Men were still standing on the lunar surface when the decisions to end it were made. Not paused, ended, while the moon still had astronauts walking on it. That cancellation did more than close out a flight schedule. It set off a second, quieter loss, one that would not be fully understood for decades. When the Saturn V line shut down, the people who had built it did not stay frozen in place, waiting for a restart that never came. Engineers retired. Some moved into other industries. Suppliers reorganized their factories around contracts that had nothing to do with the rockets. The manufacturing processes that had taken years of trial and error to perfect. The specific welding techniques. The exact tolerances. The small corrections a machinist learns only by doing the work thousands of times were never fully written down for a future team to inherit. Nobody thought they needed to be. The people who knew them were still alive, still working, still available to ask. A manual can record a measurement. It cannot record the feel of a weld that a technician's hands learned over 1,000 repetitions. This mattered more for the Saturn V than it would have for almost any other machine, because the Saturn V existed nowhere else. It had been built for one purpose, by one organization, over 1 decade. Once that decade ended, so did the only place that knowledge had ever lived. Decades later, NASA tried to go back and understand it. Engineers working on the Ares program, and later the Space Launch System, needed to know how the Saturn V's first stage engines, the F1 engines, had actually been built. The assumption going in was reasonable enough. A rocket that flew successfully 13 times must have left behind a complete technical record of how to build another one. What they found was not a filing cabinet of missing paperwork. Some manufacturing techniques were simply unknown. The engineers who knew them were mostly dead or elderly. The documentation was incomplete. The production records had scattered across archives, Nobody had organized with a future team in mind. Wait, NASA had to reverse engineer its own rocket from museum pieces. Engineers disassembled preserved Saturn V components and studied them with modern tools, trying to recover, decades later, techniques that had once been ordinary knowledge on a factory floor. The world's most powerful rocket, a machine that had flown successfully 13 times, had to be rebuilt from artifacts behind museum glass, because the people who once knew how to build it were gone. This is not a story about sloppy record-keeping, though the records were imperfect. It is a story about the limits of documentation itself. Complex machinery is never fully captured on paper. It lives in the hands and the memory of the people who make it. In judgments a machinist or a welder or a test engineer makes, without writing them down. Because in the moment, those judgments do not feel like knowledge worth recording. They feel like just doing the job. A blueprint can specify a tolerance. It cannot explain why an experienced welder backs off the heat half a second earlier on one particular joint. A correction learned through failure and never entered into any manual because it never occurred to anyone that a manual would someday be all that was left. When those people retire, or move on, or die, that judgment does not wait in a drawer somewhere for the next generation to find. It disappears with them. Capability, once built, is often treated as permanent. Something a civilization can pause and later resume exactly where it left off. That assumption does not survive contact with what actually happened to the Saturn V. Knowledge and capability degrade the moment a program ends. They do not sit preserved in storage, waiting patiently for someone to fund their return. They erode, quietly and irreversibly, the same way a skill fades from a hand that stops practicing it. So the cancellation of Apollo was never just the cancellation of 3 missions. It was the erasure of a kind of knowledge that cannot be rebuilt from what was written down, only relearned, slowly and expensively, by people starting over from artifacts under glass. And that erosion, once set in motion on a factory floor in 1968, would not stay confined to American rockets alone. It would happen again on the other side of the planet to the one other nation that had ever built the capability to leave Earth behind. That other erasure, on the far side of the world, would take its own decade to unfold. Closer to home, a different kind of loss was already underway. Not the loss of what Apollo had built, the loss of what should have come after it. After Apollo ended, the plans on the table were serious, and they were coherent. A large permanent station in Earth orbit, built to hold dozens of astronauts. A reusable shuttle to service that station, fly to it and from it routinely, and make reaching orbit cheap, the way a bus route makes crossing a city cheap. A permanent base on the moon, built on everything Apollo had already proven about landing, working, and surviving there. And eventually, a human mission to Mars, using the moon as a stopping point along the way. A place to refuel and resupply before the longer journey outward. Each piece was meant to build on the one before it. Station, then shuttle, then base, then Mars, using infrastructure and knowledge that would never have to be built twice. That is not what happened. What happened instead was a negotiated compromise, and compromises rarely preserve everything they touch. The station was deferred indefinitely at first, and would not exist in any real form until the International Space Station arrived in the 1990s, under circumstances nobody in 1972 had planned for and with a different set of partners entirely. The lunar base was abandoned outright, never built, never seriously funded again. The Mars mission became a perpetual aspiration, proposed again and again over the following decades, studied, budgeted on paper, and funded not once. Only the shuttle survived the negotiation, but surviving came at a price. With the station gone, the lunar base gone, and the science platform they would have provided gone with them, the shuttle was handed all their jobs at once. It became the program's workhorse, carrying crews and cargo on every kind of mission NASA still had. It became the military's satellite launcher. It became the commercial satellite launcher. It became the science platform that no longer existed anywhere else, a laboratory bolted into its own cargo bay. The shuttle became everything, because everything else had been cancelled. And in becoming everything, it was optimized for nothing. Here is what it was promised to do. 50 flights a year at roughly $10 million a flight, a vehicle that would make reaching orbit as routine as a cargo plane makes freight, launching almost weekly, priced like an airline ticket for hardware. Here is what it actually did. 9 flights, in its best year. An average cost of more than $1 billion a flight, across the life of the program. $10 million was supposed to buy about 20 houses. What it actually cost, more than $1 billion, could have bought 2,000 houses for one flight. And the gap was not a failure of engineering. The shuttle was an extraordinary machine, arguably the most complex flying vehicle ever built. A winged orbiter, a giant fuel tank, and 2 strap-on boosters all working in concert. The gap was a failure of everything that had shaped its design before a single bolt was tightened. Some of that shaping came down to a single choice about saving money early. The solid rocket boosters, the 2 white cylinders strapped to the external tank, were added mainly to cut development cost. Solid rockets could be manufactured by a supplier in Utah. That supplier's congressional delegation carried real weight over NASA's budget. The choice was not about propulsion. It was about politics wearing an engineering disguise, and it would sit quietly on the vehicle for 14 years before anyone paid its full price. But here's where it gets strange. On January 28th, 1986, those same boosters caused the Challenger disaster. 7 astronauts died that morning. The seal that failed had been a known risk for years, flagged, argued over, and launched anyway. And the decision that put that seal there in the first place, the decision to build those specific boosters in that specific way, was not made in 1986. It was made in 1972. Not an engineering failure alone. A budget negotiation 14 years removed from its consequence, arriving on schedule. That is the second structural cause, and it follows directly from the first. The program built to replace Apollo was compromised from its own beginning by the same forces, the same budget constraints, the same political fragmentation of technical decisions that had ended Apollo in the first place. A rocket is not supposed to carry the fingerprints of a congressional map. This one did, and 7 people paid for it. The Air Force added a further distortion of its own. The Department of Defense had become a major stakeholder in the shuttle program, and the Air Force needed to launch its own payloads, spy satellites, communication satellites, early warning satellites from polar orbits used for reconnaissance. So the shuttle's design changed again. A larger payload bay built to carry the Air Force's heavier hardware. Cross-range capability, the ability to glide far off its entry path and land after a single polar orbit, instead of waiting for the Earth to rotate back underneath it. None of it built for science, none of it built for exploration. Built because the Air Force's budget was propping up NASA's insufficient appropriations, and the Air Force's price for that money was influence over the design. The Air Force went further still. It built its own shuttle launch complex at Vandenberg Air Force Base in California. Finished in 1985, purpose-built for military polar launches, its own pad, its own gantry, its own crews trained and ready. Then, Challenger happened. NASA stopped flying military payloads on the shuttle entirely. The Air Force's involvement was supposed to strengthen the shuttle program, not more capability, not more reach. A distorted design and a launch complex finished, staffed, and never used. One of the most expensive launch facilities ever built, ready for a mission that never came, standing empty on the California coast. None of this was really about the shuttle. It was about what happens when a technology program gets built by the negotiation between competing interests instead of by a single coherent goal. A station deferred, a base abandoned, a rocket asked to be 4 different machines at once, and a launch complex built for a mission that never flew. Vandenberg was not a strange exception to how the program worked. It was the plainest evidence of how the program worked, and it would not be the last. That pattern did not stay contained to one abandoned launch pad. Widen the lens from Vandenberg to the whole way the country builds rockets, and the same shape reappears at a scale that touches every mission since. Start with the plainest requirement of all. Returning to the moon requires, at minimum, a rocket that can lift the necessary mass off the ground and out of Earth's gravity. No amount of political will, no clever mission plan gets around that. The Saturn V could carry about 130 metric tons to low Earth orbit, the near-Earth zone every deeper mission departs from. That is roughly the weight of 100 small cars, lifted as a single load, in one launch. No rocket built since has matched it. The Soviet Union tried. Its N-1 moon rocket, developed to compete directly with the Saturn V, failed in 4 consecutive unmanned tests, each one ending in an explosion on or above the pad, and the program was cancelled in 1976. The competing superpowers' own heavy lift ambition ended in wreckage, not in orbit. The Space Shuttle, America's own next attempt, was never built to match that number in the first place. It could lift about 24 metric tons to that same orbit, less than 1/5 of what the Saturn V carried. Both nations had already proven once that a rocket of that scale could fly. Neither found a path back to it, only smaller or nothing at all, not surpassed, not equaled, not even approached. Between 1972 and 2022, 50 years, no American rocket exceeded 70 metric tons to low Earth orbit, roughly half of what one Saturn V could carry, half a century earlier. An entire generation of engineers was born, trained, and retired during that drought, without ever building a rocket as capable as the one their grandparents' generation flew to the moon. The capability existed once. It did not carry forward. Reaching that same lifting power again took another rocket program entirely, built from the ground up, decades later. The rocket meant to finally close that gap is the Space Launch System, SLS, built to carry NASA's Artemis missions back to the moon. It flew its first unmanned test in November 2022. In its current configuration, it lifts about 95 metric tons. Larger versions, planned but not yet built, would eventually match or exceed Saturn V's number, on paper. Not stronger, not faster to build. 95 metric tons instead of Saturn V's 130, and far longer to build it. Saturn V went from drawing board to launch pad in 7 years, at a total program cost of about $50 billion, adjusted to today's money, covering 13 flights. Walk through that arithmetic slowly. Divide 50 billion by 13, and each Saturn V launch cost roughly $3.8 billion. SLS needed $23 billion just to fly once. A single flight, not a program. Divide that 23 billion by the 3.8 billion each Saturn V cost, and the answer is about 6. 6 times the cost, for a rocket that lifts less than Saturn V lifted, half a century earlier. Here is the number that makes the gap impossible to explain away as inflation. SLS costs roughly $20,000 to $30,000 for every kilogram it puts into orbit. SpaceX's Falcon 9, flying routinely today, does the same job for about $2,700 a kilogram, already a fraction of the government's price. Starship, still in development and testing, is designed to eventually do it for $100 a kilogram or less, if full reusability works the way its engineers intend, with a payload that could exceed 150 metric tons. More than Saturn V ever carried? That figure is a design goal, not yet proven in operation, but the gap it is aiming at is already staggering. $100 a kilogram is about what it costs to check an overweight suitcase at the airport. $20,000 for that same kilogram on the government's rocket is about the price of a new compact car, bought outright, for every kilogram. A crude lunar lander alone can weigh many thousands of kilograms, and the gap gets stranger the closer you look, because it is not, at its root, a story about better engineering. It is a story about who has to pay when a rocket goes over budget, and who benefits when it does. SpaceX builds rockets with a fraction of the workforce NASA's traditional contractors employ, inside a culture that treats a failed test as data, not disaster, and with its own money on the line, real financial pressure to find the cheaper way through. NASA's traditional contractors, Boeing, Northrop Grumman, Aerojet Rocketdyne, build under a different arrangement entirely, called a cost-plus contract. The government pays whatever the rocket actually costs to build, however much that turns out to be, then adds a guaranteed profit margin on top of that final number. Under that arrangement, a higher final cost is not a failure to be corrected. It is more profit. The incentive does not reward speed, and it does not reward savings. It rewards complexity, delay, and a bill that keeps growing, because every dollar added to the bill is a dollar the contractor keeps a share of. A schedule slip that would sink a company spending its own money becomes, under cost plus, simply another change order, another invoice, another year folded quietly into the timeline. This is the third structural cause, and it is the plainest one yet. Not a shortage of engineering talent, not a law of physics standing in the way. The institutions and contracts through which the United States builds its most ambitious rockets are shaped, deliberately or not, to reward the opposite of efficiency. Two more causes are still ahead. The rocket, in other words, was never physically impossible to build efficiently. It was arranged, contract by contract, appropriation by appropriation, not to be. No law of orbital mechanics required any of it, not the price, not the delay, not the six-fold gap between what one flight cost then and what one flight costs now. And even if a cheaper, more capable rocket had existed all along, it would still only be a ride. The place it was built to reach had barely been touched at all. Set the rockets aside for a moment and look at what they were built to reach. The moon is the closest other world we have, about a quarter of Earth's diameter. It has no atmosphere, no surface liquid water, almost no geological activity of its own, no plate tectonics dragging continents apart, no volcanoes resurfacing old ground, and its surface has sat largely undisturbed for billions of years. None of that makes the moon sound especially interesting on its own. A quiet, dry, unchanging rock does not sound like a scientific prize, but that last fact, the stillness, is exactly what makes it one. That stillness matters more than all the others combined. Earth erases its own history as a matter of routine. Wind and rain grind mountains down to gravel. Moving plates drag old crust back into the mantle and melt it. Fresh lava buries whatever came before. The oldest intact pieces of Earth's original crust, still standing today, are about 4 billion years old. And they are rare, broken, and scattered. Earth kept almost none of its own baby pictures. The moon kept nearly all of it. Once the solar system's early bombardment of debris tapered off, about 3.8 billion years ago, the lunar surface stopped changing in any major way. The pale highland regions, the bright cratered ground visible from your own backyard on a clear night, are 4 to 4.5 billion years old. Not remnants, not fragments, an original crust, preserved intact since the earliest chapter of the solar system's history, sitting exactly where it formed. Picture the moon's history compressed into a single year. The heavy bombardment ends by the 3rd week of January. Everything after that, nearly the entire rest of the calendar, unfolds across the highlands, without one major reshaping event. Earth has no equivalent stretch of quiet to show you. The moon does, and it has been showing it to us the whole time. That preserved record reaches further than lunar geology. The same bombardment that scarred the moon's face also struck the young Earth during the very period when life was first taking hold here. Earth's own record of that era is gone, worn down and buried long ago. The moon's copy of it is not. Ask what conditions surrounded life's first appearance on this planet, and the honest answer is that Earth itself no longer holds the evidence. The moon, sitting quietly next door, still does. Apollo returned about 382 kilograms of that record, roughly the weight of a grand piano, carried home from the surface. It was enough. Analysis of that rock produced the leading model for how the moon itself came to exist. The giant impact hypothesis. The idea that a young Earth collided with a Mars-sized world early in its history, and the debris from that collision became the moon. The chemistry supports it directly. Lunar rock looks like Earth's own mantle, but missing certain volatile elements, exactly what a shared, violent birth would leave behind. The lighter material boiled away by heat no ordinary geological process could produce. None of that came cheap or easy. It took years of laboratory work, spread across multiple countries and multiple generations of instruments, to read that story out of a handful of grey rock. And it rewrote the standard account of how our own world came to have a moon at all. But here's where it gets stranger. 382 kilograms is almost nothing. Spread across a surface a little smaller than North and South America combined. And all of it came from the same kind of place. 6 landing sites, everyone near the equator. Everyone chosen because it was flat and safe to set a lander down on, not because it was scientifically interesting. Not the poles, not the deep polar craters, not the region that would turn out to matter most. Here is what Apollo missed. In 1994 and again in 1998, 2 robotic missions, Clementine and Lunar Prospector, picked up a signal from craters near the poles that never see sunlight, a signal consistent with buried water ice. In 2009, a 3rd mission, L-Cross, deliberately crashed a spacecraft into one of those permanently dark craters near the South Pole and confirmed it directly. Water ice, along with traces of sulfur dioxide, mercury, and silver, sealed inside ground that has never once felt sunlight. Water changes everything about what that ground can offer. Split apart by electricity, water becomes hydrogen and oxygen, breathable air, and rocket fuel made from local ice instead of hauled up from Earth at enormous cost. A base near the pole would not need to import its own air or its own fuel. It could make both, on site, from what was already sitting there, using the resource already in front of it instead of hauling every ounce of it from Earth. Not a minor find. The single most useful resource ever discovered on the moon. Everything else Apollo brought home told us where the moon came from. This told us whether anyone could ever live there. And it was confirmed 37 years after the last human being left its surface. That gap is bigger than it sounds. If the 1969 plan for a permanent lunar base had gone forward through the 1970s and into the 1980s, instead of Apollo ending in 1972, that same water ice would likely have been found decades sooner, by astronauts already living and working near the poles, not by an unmanned probe watching from orbit 4 decades late. The equipment to use it, splitting it into air and fuel and putting both to work, would be old and proven by now instead of still being tested for the first time. A polar base that could have been supplying its own crews with homemade air and homemade fuel since sometime in the 1980s is, instead, still a proposal on paper. The 50-year gap did not just cost missions that were never flown. It cost decades of understanding a world we had already reached once, then left alone. Every year of that absence was a year the poles sat there, ice and all, unvisited and unused, while the equipment and the experience that could have unlocked them were never built. Whatever else went wrong on the road back to the moon, that loss is quieter than any budget line, and easy to miss entirely, hidden in the space between what Apollo did learn and what it never had the chance to. The United States was not the only nation that reached this far and then let the reach slip. The Soviet Union lost the moon race outright. Its own giant rocket, the N-1, failed in 4 straight unmanned tests, one of them ending in an explosion on the launch pad large enough to level a small town, and it never carried a cosmonaut anywhere near the moon. No Soviet boot ever touched lunar dust. That was a real geopolitical defeat. A public loss of the one contest the Soviet Union had staked its scientific reputation on since Sputnik first crossed the sky. But here's where it gets strange. Losing did not mean stopping. It meant turning. The Soviets pivoted to a domain where they could still win, not reaching a place once, but staying in space longer than anyone else ever had. The Salyut program began in 1971, a series of orbiting stations built to keep cosmonauts aloft for months at a stretch instead of days. Mir followed in 1986, bigger, longer-lived, assembled piece by piece across nearly a decade until it resembled less a single spacecraft than a small orbiting complex of connected rooms. Cosmonaut Valery Polyakov spent 437 consecutive days aboard it, more than 14 months without touching solid ground, a single stretch of endurance that stood as the record for years afterward. He went up able-bodied and came home having proven a human being could survive the trip to Mars and back, at least in terms of time spent weightless, without the body giving out. Not idle, not conceding the field, choosing a different contest, one with no fixed finish line, and simply staying ahead in it. That choice produced real knowledge, and it was not trivial knowledge. How the human body changes across months in freefall. The bone that thins, the fluid that shifts toward the head, the muscle that has to be fought for daily, with hours of forced exercise just to walk again on landing. How to recycle air and water inside a sealed metal can, with no resupply for weeks at a time. What isolation does to a crew that cannot step outside, cannot go home, cannot even open a window, confined with the same 2 or 3 faces for a year at a stretch. Some of that knowledge crossed over directly into the International Space Station once the Cold War ended and the 2 former rivals began sharing hardware and procedure. Soyuz, still the vehicle NASA itself relied on to reach that station for years. Some of it did not survive to make the crossing. The Soviet Union collapsed in 1991, and the consequences arrived immediately. Russia inherited the rockets, the launch pads, decades of flight experience, on a fraction of the old budget. Whole programs were shelved outright. A reusable shuttle of its own called Buran flew once, unmanned, in 1988, and never flew again. Quietly cancelled as the money ran out. Engineers left for other countries or left the field altogether. Some hired away by the very space agencies that had once been rivals. The knowledge that lived in their hands and their judgment, not in any manual, thinned out the same way it had at the Saturn V line 2 decades earlier, an ocean away, for the same underlying reason. A program stops, and the people carrying its knowledge scatter before anyone finishes writing it down. What remains is a diminished version of a once formidable program. Russia has kept the Soyuz capsule and its launch vehicle flying reliably for decades. A dependable way to move crew to and from orbit, plain and unglamorous and consistently effective. And it still helps operate the space station its old rival now shares with it. But nothing beyond Earth orbit has followed. No lunar mission. No serious plan for one that survives contact with a budget. The ambition to attempt it simply is not funded, and nothing on the horizon suggests that changes soon. Ask which of the two original superpowers could mount an Apollo-class mission today, on short notice, with the people and the hardware currently on hand, and the honest answer is neither one. Not the country that put 12 men on the moon, not the country that kept a human being in orbit for 437 straight days. Both spent the intervening decades proving something real, and both, in the process, let the specific capability that made the original race possible thin out past the point of easy recovery. This is the fourth structural cause, and it belongs to both sides of the old race, not just one. The two nations that once built rockets capable of leaving Earth entirely no longer have the standing capability to do it again on their own terms. Not because the physics changed, not because the moon moved further away, because the people who knew how, on both sides of an ocean and an old ideological line, retired, emigrated, or simply moved on to other work, and what they knew went with them, undocumented, unrecoverable, gone the ordinary way. A skill disappears when the hands that held it stop working. Capability does not wait patiently in storage for someone to come back for it. It erodes the moment the people who hold it stop being paid to use it. Quietly, without a headline marking the day it happened. Returning to the moon today would be harder than it was in 1980. Not because the destination changed or the physics got stricter, but because both nations that once knew the way there in their bones have partly forgotten it. One launch pad, and one retirement at a time. One structural cause remains, and it may be the deepest of the five. Not a rocket, not a budget line, not an engineer's retirement. A question about what kind of promise a country has to make to itself before it will actually keep going. A promise like that has a shape. Apollo's had 3 edges to it, and losing even one of them turned out to be enough to end everything that tried to follow. Start with what Kennedy actually committed to in 1961, standing in front of Congress and describing a goal with almost no room to hide inside. Land a man on the moon, bring him home safely, do it before the decade closed. Nothing about that was aspirational language dressed up as policy. It was a test with a pass condition anyone could check. Feature 1 was specificity. Either a man stood on lunar ground before December 31st, 1969, or he did not. There was no partial credit, no redefining success halfway through, no quiet moving of the goalposts. Progress could be measured against that line every single year, which meant it could also be defended every year in front of a Congress that had to keep funding it or explain publicly why it had stopped. A vague goal gives a skeptical lawmaker an easy exit. This one did not offer one. Feature 2 was the deadline itself. 8 years before the decade was out, long enough to actually build the hardware. Short enough that no administration could hand the hard decisions to some distant successor. A goal with no clock drifts. This one could not. Every year that passed narrowed the runway instead of lengthening it, and that narrowing became its own source of pressure, keeping the money moving when it might otherwise have stalled. 8 years also sat inside a horizon a politician could actually see, close enough to matter to the people who had to keep signing the checks, far enough away to leave room for the engineering to catch up. Feature 3 was the stakes sitting underneath the other two. This was never really a science competition. It was read correctly as a proxy contest over which political system could outbuild the other's missiles, in an era when missiles were how a nuclear standoff got settled, without anyone actually launching one. Losing would not have simply stung. It would have read to allies and adversaries alike as evidence of weakness at exactly the moment neither superpower could afford to look weak. Specific, bounded, existential. 3 features working together, and together they built something sturdier than any one of them could alone. Strong enough to survive budget fights, a change of president, and a war in Vietnam pulling the country's attention sideways. It even survived the trimming at its own edges. 3 later missions cut for money and politics, without the core promise itself ever breaking. A man still stood on the moon before the decade closed. That was the part nothing was allowed to touch. Nothing built since has carried all 3 features at once. Here is the pattern instead. Return for science. Establish a presence. Develop capabilities for an eventual Mars mission. Worthy phrases, every one of them, and every one of them soft enough to bend whenever a budget year got tight. Which one counts as success? All of them, technically. None of them in practice, because none of them has a date attached, or a line that gets crossed in public, or a visible failure the day it slips. A goal that cannot be checked against a calendar can always be redefined instead of defended. And a program built on a redefinable goal is a program built to be deferred indefinitely, without anyone ever having to say so out loud. The deadlines tell the same story from another angle. In 1989, the Space Exploration Initiative promised a moon return by 2004 and a Mars mission by 2019. Neither happened. In 2004, the vision for space exploration promised a moon return by 2020. That did not happen either. Artemis was supposed to land astronauts by 2024. That date slipped to 2026, and it may slip again before it is done slipping. Each of the 3 borrowed Apollo's language almost exactly. A bold destination, a page in the calendar. And each time the page arrived with nothing launched, the response was never to admit the program had failed. It was to print a new page and move on as if the old one had never been promised at all. 3 different presidencies, 3 different decades, the same outcome landing every time. Not cancellation, exactly. A kind of permanent postponement wearing a schedule as a disguise. And the 3rd feature simply is not there to replace. The Soviet Union that made 1969 feel existential does not exist anymore. China runs a serious lunar program of its own, but it has not yet produced the kind of fear that once moved a country to spend more than 4% of its entire federal budget on rockets inside a single decade. Maybe it will. Not yet. And until it does, there is nothing standing behind a moon program the way a nuclear-armed rival once stood behind Apollo, watching, keeping score, forcing an answer. Without that fear, deferring a moon return costs a politician almost nothing. No opponent points to an empty launch pad in a campaign ad. No headline calls a delay a defeat. The cost of waiting one more year stays invisible, so waiting keeps winning the argument by default. This is the 5th structural cause, and of the 5, it may be the deepest. Not a shortage of money. A shortage of a particular kind of promise. One specific enough to fail visibly. Dated enough to force a reckoning. And expensive enough to break that nobody wanted to be the one who broke it. Every dollar Apollo spent flowed through a promise built that way. Every dollar spent since has had no comparable channel to flow through. So it has drifted, year by year, toward whatever was easiest to defend in the moment, rather than what the moon actually required. Money can buy hardware. It can buy engineers, launch pads, years of testing. It has never, on its own, bought the specific, dated, existential kind of promise that keeps a program from quietly dissolving the first time a budget gets tight. None of this happens by accident, though. Somewhere underneath the missing promise sits the ordinary machinery that decides, year after year, exactly how much a country is willing to spend, and on what. That machinery has a shape of its own. It has been quietly setting the terms for every decision this far, long before anyone ever stood up to make a promise at all. That machinery starts with a number nobody thinks of as a number. Every choice that trimmed Apollo, that boxed in the shuttle, that deferred the lunar base year after year, that took a decade and tens of billions to build a rocket that still hasn't flown astronauts, was in the end a choice about money. Not a failure of nerve. Not a single villain sitting in an office deciding the moon wasn't worth it. A budget line, moving up or down, the way budget lines move in a democracy. That is worth sitting inside for a moment, because it is easy to miss. A government does not simply decide what it values and fund it. It divides a fixed pool of money across healthcare, defense, infrastructure, education, and everything else competing for the same dollars, and whatever slice space gets is a rough measurement of how the population weighs it against all the rest. The budget is not separate from the story. The budget is the story, expressed in percentages instead of paragraphs. In the 1960s, that slice reached roughly 4.5% of the entire federal budget, already translated once. But the number that matters here isn't the size. It's what kind of number it was, not a baseline, not a level a healthy space program simply operates at. A wartime allocation sustained only because Soviet rockets read as a direct threat to national survival. The same missiles that could carry a bomb could carry a man, and a country does not fund that kind of fear at a normal rate. Then the fear went. The Soviet Union stumbled, its own moon rocket failing test after test, and the United States had already won the only contest that mattered. The political case for wartime spending didn't erode slowly. It simply had nothing left to stand on. And the budget did what budgets do when the reason for their size disappears. It reverted. It reverted to about 0.3%. That is where it has sat, roughly, ever since. Enough to keep the International Space Station running, enough to fund a steady stream of robotic science missions, enough, over more than a decade, to build one new heavy-lift rocket. Not enough on its own to build a lunar base and keep it running. Not enough to mount a Mars mission on any real timetable. The peacetime number and the wartime number were never the same kind of thing, and mistaking one for the other is most of why just fund it properly sounds simpler than it is. Here's where the machinery gets specific. The fraction has moved since, a little higher under one administration's vision, a little lower under the next, higher again when Artemis got its funding, roughly level after that, but it has never climbed back toward the Apollo number. It rose a little under George W. Bush's vision, fell under Obama, rose again when Trump funded Artemis, and has held roughly level under Biden. And without something with the force of Sputnik behind it, there is no obvious reason it would keep climbing. What a sustained lunar return actually needs is a number that sits in between, above peacetime, below wartime, held there for longer than any one president gets to hold power. American politics is not well built for that. A commitment has to survive a 4-year cycle, then an 8-year one, then whoever comes after, and almost nothing does. Congress is where that instability gets resolved into something concrete, and not always for the better. A president proposes a budget. Congress writes the actual one. By 1969, Richard Nixon wanted NASA's funding cut hard. Apollo had done its political job, the flag was planted, the race was won, and in his view, there was no further reason to keep paying wartime prices. But NASA had defenders in Congress who were not weighing exploration against national prestige. They were representatives from Texas, Florida, Alabama, and Ohio, states with NASA centers and NASA payrolls, and their voters' jobs mattered more to them than any argument about the moon. What came out of that negotiation was neither Nixon's number nor NASA's wish list. It was a compromise. The lunar base got deferred. Apollo got shortened. The shuttle got funded, because the shuttle could be sold as keeping those jobs alive. That same pattern, protect the jobs, adjust the mission to fit, never fully died. Look at the space launch system. When the Obama administration cancelled its predecessor program in 2010, Congress didn't let NASA start over with a clean design. It wrote the replacement's requirements into law. Requirements that pointed straight back at the old contractors and the old buildings. The core stage would be built at the Michoud facility in Louisiana. The engines would come from Aerojet Rocketdyne's plants in Mississippi and Alabama. Final assembly would happen in the same vehicle assembly building at Kennedy Space Center that once stacked Saturn V. Those facilities employed tens of thousands of people in states whose representatives had every reason to keep it that way, and the law made sure they could. Not a technical decision. A political one wearing a technical decision's clothes. That is the reveal underneath the price tag. SLS costs roughly $4 billion for a single launch, not because heavy-lift rockets are inherently that expensive, but because it was built inside a legal structure designed to preserve specific jobs at specific facilities rather than to minimize cost. Compare it to Starship, developed at SpaceX's own site in Boca Chica with none of those obligations, aiming for a per-launch cost in the tens of millions if full reuse holds up. Same rough job, a rocket that gets people and cargo off the planet. Wildly different price, because one was optimized for efficiency and the other was optimized for political survival. Call it what it actually is. Not corruption, not in the way that word usually gets used. Something more ordinary and, in its way, more durable. Economists call it concentrated benefits and diffuse costs. The workers at Michoud, at the Aerojet plants, at every facility SLS keeps running, feel the benefit directly in a paycheck, and they organize hard to protect it. The cost lands on everyone else, spread so thin across every taxpayer in the country that no single person feels it enough to fight back. Nobody has to break any law for that arrangement to hold. It is simply what happens, again and again, when a few people have everything to gain from a decision and everyone else has almost nothing individually to lose, which is the real diagnosis, once all of it is laid out plainly. The failure to return to the moon was never mainly a story about missing engineering. The engineering existed in the early 1970s, and versions of it have been rebuilt since. It is a story about the machinery democracies used to decide, year after year, how much to spend and who gets to spend it, and that machinery has never once, since 1972, produced the kind of number the moon actually requires. Whether the newest attempt, spread across commercial partners and international allies instead of concentrated in a handful of congressional districts, can survive that same machinery is still an open question. What isn't open is what the machinery has cost so far, and that cost has a name, a mission number, and a launch date that never came. 3 of those mission numbers were Apollo 18, Apollo 19, and Apollo 20. Apollo 18 was supposed to land in Schroeter's Valley, a long winding channel cut into the surface not by water, but by an ancient river of lava, frozen in place. The plan was to reach subsurface rock no earlier mission had touched. Rock that could finally explain the moon's volcanic past, how it flowed, how long it lasted, how deep the record of it actually ran. Apollo 19 was aimed at the Hyginus Rill, another lava channel, this one paired with a longer-range rover built to travel 100 kilometers or more across the surface, farther than a full day's drive on a highway back home. Apollo 20 was aimed at Tycho, one of the youngest and deepest large craters on the moon, barely 108 million years old, against a surface where most rock runs into the billions. Its central peak, promised something rare, material thrown up from deep inside the crust by the force of the impact itself. No rover, no drill, and no laboratory on Earth has ever touched a sample from that deep. Not 3 repeats of the same landing. 3 separate bets on 3 separate mysteries. Volcanic history, the deep crust, a young crater's violence. All 3 cancelled in 1970. The samples were never collected. The hypotheses were never tested. 50 years later, they are still hypotheses. Whatever Schroeter's Valley or Tycho's Central Peak would have shown, nobody alive today has seen it. And nobody currently has a mission planned to go look. The program meant to carry Apollo's hardware forward fared no better. The plan was to turn surplus rockets and modules into extended lunar operations, mobile laboratories that could roam far past a single landing site. The beginnings of a permanent base built up mission by mission until astronauts could stay for months instead of days. Almost none of it survived the cuts. What did survive became Skylab, a station built from a spare Saturn V third stage, hosting 3 crews through 1973 and 1974. The mobile labs and the permanent lunar construction stayed exactly what they had always been on paper: plans, cancelled before a single piece of hardware was built. Houston built a facility to match Apollo's ambitions, not its ending. The Lunar Receiving Laboratory was designed to process hundreds of kilograms of moon rock, shipment after shipment, for years into the future, built on the assumption that Apollo was a beginning rather than the whole of it. It received 382 kilograms from 6 missions, and then nothing further. Not a slowdown, a stop. Rooms built for an ongoing program sat waiting for cargo that stopped arriving in 1972, and did not arrive again for 5 decades. The same kind of built and abandoned infrastructure as a launch complex in California that never launched anything. Something similar happened to the resources the moon was quietly holding the whole time. Scientists suspected water ice at the poles as early as the 1970s. The physics was simple enough to work out on paper: craters near the poles that never see sunlight, cold enough to trap water for billions of years, if any water ever arrived there to begin with. Working out that it was possible was not the same as confirming it was true, and confirming it took decades nobody had a good reason to spend. Clementine found the first hints in 1994. L. Cross delivered the proof in 2009, driving a spent rocket stage into a permanently shadowed crater near the South Pole and watching the debris plume for the signature of ice. It found it. L. Cross itself was small and cheap, as space missions go. The kind of mission that could have flown in the 1970s if anyone had thought it worth prioritizing. Not a discovery science only made in 2009. A discovery politics deferred since the 1970s. Confirmed decades late. That ice was knowledge that would have been transformative in 1975. Sitting unconfirmed for more than 30 years, not because it was undiscoverable, but because nobody sent the mission to look. Had the lunar base planned in 1969 actually been built through the 1980s, that ice would almost certainly have been found and confirmed 30 or 40 years sooner, and the technology to put it to use would already be mature instead of just beginning. The Lunar Reconnaissance Orbiter, launched in 2009, mapped the whole moon down to 0.5 meter per pixel, sharp enough to pick out the abandoned equipment still sitting at every Apollo site. That map would have been priceless to a base operating in the 1980s, telling planners exactly where to land and where the ice actually pooled. Instead, it arrived roughly 40 years after it would have mattered most, describing a moon that a sustained program would already have been living on. Each of these delays did the same quiet thing. It postponed the knowledge and actual decision needed. Not just missions that never flew, but decades of understanding that never arrived with them, one deferred discovery pushing the next deferral further down the line, compounding rather than resetting. A program running continuously does not just keep flying, it keeps learning, and every year of that learning changes what the next decision even looks like. None of that accumulation happened. It sat frozen at 1972 levels, while the questions it could have answered kept waiting, and every plan drawn up since has had to work with less than it should have known by now. A mission number and a delayed discovery are the kind of loss that shows up in a list, countable, dated, precise. What went missing next did not show up in any list at all. What went missing next was not a mission number or a rock sample. It was a belief a whole generation carried and then quietly had to set down. In July 1969, roughly 650 million people watched Apollo 11 land on the moon, live, on television. That is close to 1 in every 5 people alive on the planet at that moment, all of them looking at the same grainy picture at the same time. Nothing before it had gathered that much of humanity around a single live event. Not a coronation, not a war's end. A man stepping down a ladder onto another world, watched by a fifth of the species he belonged to. Watching it did something to people that a written account of it never quite explains. This was not a story about a dream. It was a dream, happening, in real time, on a screen in a living room. And the natural conclusion, sitting in that living room in 1969, was simple. If a species could do this with 1969 technology, slide rules, punch cards, computers weaker than a modern calculator, then the years ahead had to bend upward from here. Mars by 1980, maybe 1990. Space stations circling overhead, lunar trips as routine as an airline flight, interplanetary travel arriving on the same accelerating schedule that had just put a man on the moon. That expectation did not stay confined to speeches and newspaper headlines. It became the culture itself. Through the 1970s, science fiction moved from a niche shelf to the center of the popular imagination. Star Wars, Star Trek, 2001. A space odyssey, each one assuming, almost casually, that humanity's future ran outward, toward orbit, toward other worlds, toward exactly the direction Apollo had just proven possible. The genre was not inventing a hope out of nowhere. It was reflecting one that already existed. One Apollo had planted in thousands of screenwriters and millions of viewers at once. The picture did not hold. The future those stories kept promising never showed up. Not by 1980. Not by 1990. Not ever, at least not on the schedule, a fifth of the world had watched get set in 1969. By the late 1970s, then more plainly through the early 1980s, it became hard to avoid noticing. The shuttle was flying, but it was expensive and limited. Mars was not near. The moon was not being revisited by anyone, and no one currently in a position to send someone back seemed to be trying. There was no single announcement that the imagined future had been cancelled. Nothing so dramatic as that. It was slower and stranger than a collapse, a quiet, uncomfortable recognition spread out across a full decade, that the 1969 promise had simply stopped being kept. Space drifted out from the center of how people pictured tomorrow and settled somewhere closer to the edges, present in the culture, but no longer driving it. The vehicle meant to carry the country forward through that disappointment never had the standing to change it. The shuttle was, by design, meant to be routine, ordinary. A truck, not a voyage. And a truck, however remarkable the engineering underneath it, does not command a planet's attention the way one man's footprint on another world does. Its missions were about payloads, experiments, logistics, work that mattered without being the kind of work that gathers 650 million people around a screen. It was, or aspired to be, routine, and it was that very routineness that made it a smaller cultural object than the program it replaced. Then came January 28th, 1986. 7 astronauts died aboard Challenger, seconds after launch, on live television. Watching in classrooms across the country were school children, brought there specifically because one of the crew was a teacher, meant to be the first ordinary person to fly into space and beam a lesson back down to them. Instead, they watched the vehicle break apart in the sky. It was not only a tragedy, it crystallized every uneasy feeling that had been building around the shuttle for years. Its costs, its risks, its failure to become the affordable, routine spacecraft it had been sold as at the start. The program was grounded for close to 3 years, while investigators worked out what had gone wrong and what had to change before anyone flew again. Flights resumed in 1988. The shuttle kept flying for another 15 years, carrying crews to orbit, building the International Space Station piece by piece, doing the patient, unglamorous work it had always been meant for. For a while, it looked as though the worst was behind it. Then, in 2003, it happened again. Columbia broke apart during re-entry, its heat shield damaged during launch in a way no one caught in time to act on. 7 more astronauts died, 14 across the 2 disasters, over a program that ran roughly 30 years and never once reached the flight rate or the cost it had promised when it began. Not a steady climb towards something greater. A holding pattern, expensive and repeatedly fatal, that ended in 2011 with the shuttle's retirement, and with nothing built and ready to replace it. For the next 9 years, the United States could not launch its own astronauts into space at all. American crews rode to the International Space Station in Russian Soyuz capsules, a single seat costing the country roughly $90 million, paid to the same nation it had once raced to the moon to beat. The country that put 12 men on the lunar surface could not, for nearly a decade, put 1 man into low Earth orbit under its own power. That is the shape American human spaceflight actually took after Apollo. Not a rising line, each decade more capable than the last, the way 1969 seemed to promise. A fragile, expensive effort just to hold a foothold in low Earth orbit, twice paid for in astronauts' lives, while everything Apollo had made a generation believe was coming next. A lunar base, a Mars landing, a genuinely spacefaring future, sat perpetually out of reach. The cost of the 50-year gap was never only measured in missions that did not fly or samples that were never collected. It was measured in what an entire generation expected of its own future, and quietly, without ever being told outright, learned not to expect anymore. A disappointment that sighs invites an obvious question. If sustaining Apollo's momentum failed this completely, was returning to the moon ever actually worth the trouble? The question sounds like doubt. The answer underneath it was never seriously in question. The moon holds real value, apart from the political theatre it briefly performed in 1969, and only in the last few years have the pieces needed to act on that value actually started arriving. Start with water. Confirmed ice sits frozen at the poles, packed into craters sunlight never reaches. Water means drinking water and a way to grow food. It also means propellant and air. Electrolysis, running a current through water to split it apart, produces hydrogen and oxygen, the same 2 ingredients that fuel a rocket and fill a breathable cabin. A base built near the ice would not need every gallon shipped up from Earth. It could make its own water, its own air, its own fuel, already sitting under its own floor. That local fuel supply matters for more than the base itself. The moon sits at a useful gravitational address relative to Earth, close enough to reach in days, far enough out to serve as a jumping-off point for everything beyond it. Propellant made from lunar water can top off a spacecraft in lunar orbit before it continues toward Mars or the asteroid belt, cutting the mass that has to be lifted out of Earth's much deeper gravity well in the first place. The delta V, the change in speed an engine has to produce to get somewhere, needed to reach Mars from lunar orbit, is substantially smaller than the delta V needed from Earth orbit. A tank topped off on the moon buys real margin for a much longer trip. A third reason has nothing to do with propellant at all. Certain polar craters never see sunlight, and their floors sit close to absolute zero, colder than almost anywhere on Earth's surface. Ideal conditions for some of the most sensitive instruments astronomy owns. A radio telescope, built on the moon's far side, would sit permanently shielded from Earth's own radio noise, able to listen to long wavelengths that Earth's atmosphere blocks out entirely. And the ancient regolith of the lunar highlands has recorded billions of years of solar activity and cosmic rays, readable like a geological record of the sun's own history, one Earth's active, eroding surface never managed to preserve. Fourth, the moon is a rehearsal stage that Mars does not offer. Whatever technology a Mars mission will eventually need, life support that runs itself for years on end, pulling resources from local material instead of Earth shipments, habitats that hold up far from any rescue, can be tested and broken and fixed on the moon first, at a fraction of the risk. The moon is 3 days from Earth. Mars is 7 months. An emergency on the moon is survivable because help can still reach you. The same emergency on Mars is not because it cannot. None of this is new information. Water ice was suspected decades before it was confirmed. The staging point argument has been made since the 1960s. The scientific case for the poles and the far side has sat in proposals and papers for decades without ever quite reaching a launch pad. Not a shortage of reasons. A shortage of the structures required to act on them, the same structures earlier sections spent so long tracing the absence of. Here is what actually changed. In the Apollo era, there was no such thing as a private company with both the technical capability and the financial incentive to build its own way to the moon. That now exists. SpaceX, Blue Origin, Astrobotic, Intuitive Machines, and ISpace are developing landers, rovers, and communication relays that did not exist 5 years ago, built by companies competing for contracts rather than waiting on a single government program to fund every step. Landing on the moon had always been the work of national governments, treasuries behind them, decades of institutional infrastructure behind that. Not anymore. In February 2024, Intuitive Machines landed its Nova C lander near the lunar South Pole. It was the first American spacecraft to make a soft landing on the moon since Apollo 17 in 1972. The lander came down at an angle the mission had not planned for and tipped onto its side. It kept working anyway. It kept transmitting data from a tilted, half-fallen spacecraft for days afterward. It was the first commercial lunar landing in history, and NASA paid for it under a services contract, buying a delivery the way a shipping company buys a delivery, instead of owning and running the whole program the way it had with Apollo and with everything that came after Apollo. That is a different model. A company bears its own development cost and its own risk, competes for the contract, and has every financial reason to make the next trip cheaper and more reliable rather than more expensive. Whether that model can carry the weight of an actual return, routine landers, falling costs, a foothold that lasts, is still an open question. One this section can raise, but not yet answer. What is no longer true is that the moon sits beyond reach for lack of a reason to go. The reasons were always there. What comes next is whether the machinery finally being built to answer them is strong enough to hold. One piece of that machinery already has a name, a launch date, and a promise 5 decades in the making. It is called Artemis, after Apollo's twin sister in Greek myth, and its stated goal is explicit: land the first woman and the first person of color on the moon. Artemis 1 has already flown. In November and December of 2022, an unmanned Orion spacecraft rode NASA's new Space Launch System around the moon and back to Earth. The rocket worked. The capsule worked. A crewed lunar mission is, for the first time in decades, technically real again, not theoretical. Artemis 2 comes next, planned for 2025. 4 astronauts will fly around the moon without landing, the same shape of mission Apollo 8 flew in 1968, a lap around another world before anyone tries to stand on it. Artemis 3, planned for 2026, is the landing itself, using a SpaceX Starship vehicle to carry the crew down to the surface. It would be the first time a human being stands on the moon since Eugene Cernan climbed back into his lander in December 1972. 54 years, if the date holds. That is the number this entire piece has been circling. And here is where the same old weight shows back up. SLS, the rocket underneath Artemis, cost close to $4 billion a launch. That is not a new figure. It is the same price tag that showed up earlier as a number Congress wrote directly into law, a structure built to preserve jobs at specific facilities rather than to minimize cost. Artemis inherited that structure whole. Orion, the capsule riding on top of it, took more than a decade to develop and carries a matching price. It is a capable spacecraft. It is not a revolutionary one, not a break from the old machinery. A continuation of it, wearing a new mission name. If Artemis depended only on SLS and Orion, the 50-year gap could easily stretch into a 60-year one, funded at the same unhurried pace that killed every program before it. What makes Artemis different is what is meant to land the crew once they reach lunar orbit, and that part of the plan does not belong to NASA's traditional contractors at all. The lander for Artemis 3 is Starship, SpaceX's fully reusable stainless steel rocket, the largest and most powerful ever built. If it reaches its design goals, Starship does not just support one landing. It changes the underlying cost of reaching space by a factor of 10 to 100 against everything flying today, SLS included. A moon mission that once needed a wartime-sized share of the federal budget could cost a fraction of what Apollo cost, cheap enough to open the moon to research institutions and private companies, not governments alone. Starship is still being tested. It is still failing in places and succeeding in more of them with each flight. The booster and the upper stage have separated in flight using a technique called hot staging, igniting the next stage before the first has fully let go. The booster has flown back to the launch tower and been caught by its mechanical arms. The upper stage has done the same. Full reuse, the hardest and most expensive part of the entire equation, has already been demonstrated in pieces. If it comes together as designed, this would be the single largest drop in the cost of reaching orbit since the space age began. It would make the question this whole piece has been asking, why did we never go back? Sound almost quaint. That is conditional. Starship has not yet flown with a crew. It has not yet landed on the moon. It has not yet proven any of this holds up past a test flight. And while it is being tested, someone else is closing the distance. China has run a lunar program that rarely makes headlines and rarely misses a step. Chang'e 1 reached lunar orbit in 2007. Chang'e 4 landed on the moon's far side in 2019, a landing so difficult no country had ever attempted it before. Chang'e 5 returned lunar samples to Earth in 2020, the first sample return since the Soviet Union's Lunar 24 mission in 1976. China has now announced a crewed landing targeted for around 2030, built around a new Long March 10 rocket and a crew capsule called Mengzhou. Nothing about the pace so far suggests the date is a bluff. If China puts a human being on the moon before Artemis 3 ever flies, the symbolism reaches further than one mission. Not a footnote in a space industry newsletter. A replay of the exact scenario Artemis was built to prevent. The Soviet Union that Apollo raced no longer exists. But the shape of the contest it built, whoever plants a flag first sets the terms for everyone who follows, has outlived the country that lost it the first time. China's ambitions do not stop at a single landing. China and Russia have signed an agreement to build a permanent lunar base, the International Lunar Research Station, near the South Pole, with construction beginning this decade and crews arriving in the next one. The South Pole is not a random choice. It is the same region holding the water ice already described earlier. The region this piece has already called the Moon's most valuable real estate. And that real estate is limited. A workable site needs confirmed ice nearby, ground stable enough to build on, a clear line of sight back to Earth for communication, and enough nearby sunlight to run solar power. Put all four requirements together, and the number of genuinely good locations on an entire world shrinks to a handful. Here is the problem nobody has actually solved. The Outer Space Treaty of 1967 says no country can claim sovereignty over the Moon. It says almost nothing about who gets to occupy a site once flags give way to buildings, or who has the right to the ice sitting under someone else's landing pad. The Artemis Accords, NASA's attempt to write newer rules for lunar behavior, have been signed by dozens of countries. China and Russia are not among them, and neither recognizes the Accords' authority over anything. The landscape taking shape at the lunar South Pole is not the Cold War rivalry that shaped Apollo. It is not an empty legal question either. It looks far more like the early years of Antarctic exploration, competing claims on contested ground, with no enforcement authority standing over any of it. And the stakes are not symbolic. Not just flags and footprints, water, fuel, the handful of places on an entire world where a permanent home is actually possible. The rivalry Apollo was built to win never really ended. It only went quiet for 50 years, and it is no longer just two countries deciding how the Moon gets shared next. Two countries used to be the whole conversation. Not anymore. A dozen now have a say in how the Moon gets used, and most of them arrived quietly, one landing at a time, while the headlines stayed fixed on Washington and Beijing. None of it needed a treaty signing or a summit to happen. It happened the way most of this story happens, in engineering budgets and launch schedules, one country at a time deciding it could afford to try. The European Space Agency got there first, and it got there without a lander of its own. The Orion capsule that carried the unmanned Artemis 1 mission around the Moon and back needed a way to keep a future crew alive and moving between one world and the other. Air, power, propulsion, the systems that turn a sealed capsule into something a person can survive inside for days. Europe built that piece. It's called the service module, and without it, Orion does not fly. That single component ties European industry, European funding, and European political will directly to whether Artemis succeeds, a stake purchased with hardware rather than with astronauts. A program with partners scattered across a dozen legislatures is a harder program for any single legislature to quietly defund, which is exactly the kind of durability every purely American effort since Apollo has lacked. Japan's space agency, JAXA, has been circling the Moon with orbital missions for years and holds its own formal partnership in Artemis, one that includes seats for Japanese astronauts on future lunar surface missions. Not just a supporting role, but a claim on the surface itself. Then, Japan landed something. In January 2024, a Japanese spacecraft called SLIM touched down near the lunar South Pole, and Japan became the 5th country in history to land anything on the Moon. The landing itself was the achievement. SLIM came down within 100 meters of its intended target, about the length of a football field, a precision no earlier lunar mission had managed. That kind of accuracy matters enormously at the South Pole, where the valuable ground, the ice-bearing shadow, the workable approach path, sits in patches small enough that missing by a mile is the same as missing entirely. For half a century, this had been a two-name story. Not since. In August 2023, an Indian spacecraft called Chandrayaan-3 landed near that same pole, the first successful lunar landing anywhere since 2020, and the first landing ever that close to the south. Its rover found sulfur and other elements sitting in the polar soil. Its lander measured how the temperature changed just beneath the surface. India became the fourth country to land on the moon, and the first to do it near the pole every other country now wants. 4 different countries, 4 different sets of engineers, 4 different reasons for going. Each of these programs carries its own national interest, its own technical approach, its own appetite for risk, and none of them is simply copying what the others already did. That is what a genuinely diversified ecosystem looks like. Not one plan executed by many hands, but many plans converging on the same small patch of shadowed ground. Count it plainly, and the shift is hard to miss. In 1969, 2 countries were racing for the moon. In 2025, something like a dozen countries have lunar programs or lunar ambitions of their own, and commercial companies from several of those countries are building landers, rovers, and communication relays of their own alongside them. The rivalry that used to run through Washington and Moscow, and now mostly runs through Washington and Beijing, is still the loudest voice in the room. It is no longer the only one in it. It is not even the only one with a lander on the surface. A crowded room needs rules, and the moon currently has 2 competing sets, written by 2 different camps that do not answer to each other. More than 40 countries have signed the Artemis Accords, a set of American-drafted principles for how nations should behave on the lunar surface, share data, and avoid interfering with each other's operations. China and Russia have built a rival framework of their own around the lunar station they intend to construct at the South Pole, and neither recognizes the Accord's authority over anything they do. Between those 2 frameworks sits nothing that can actually settle a disagreement. No lunar court, no binding treaty with real enforcement behind it. Nothing but a 1967 agreement that already proved too thin to answer the harder questions about occupation and resources once anyone actually started building. The disagreement is not abstract. It is about who gets to build in the small handful of places where the ice, the sunlight, and a clear line of sight back to Earth all line up at once, and what happens when 2 flags want the same patch of shadow. That is the shape of the problem now sitting over the moon's most valuable ground. It is not a legal question anyone has finished answering, and it is not a rivalry anyone has finished running. It is a world claimed by no one and coveted by everyone, and the arrangements that will decide who gets which piece of it are still being written, in practice, by whoever gets there first and stays. It would not be the first time a fast-moving ambition outran the rules built to contain it, and it would not be the first time the ones left holding the old rules found out too late how little they were worth. History has already run this experiment once, on a much older ocean, with a much older fleet. That fleet was Chinese, and it sailed 6 centuries before anyone at NASA was born. In the early 1400s, the Admiral Zheng He commanded a fleet of treasure ships to Southeast Asia, to India, to Arabia, and down the coast of East Africa. Some estimates put his largest vessels at 5 times the size of the ships Columbus would sail 6 decades later. China had the most advanced naval technology on Earth, by a wide margin, and had already proven it could sustain a fleet at sea for years at a time. The fleet reached the African coast. Nothing stood between it and Europe, or the Americas, except the decision to keep going. The decision went the other way. The Yongle Emperor, who had sponsored the voyages, died, and the Guande Emperor who succeeded him ordered them stopped. The shipyards were closed. The records were destroyed, deliberately. The great ships were left at anchor to rot. Within a single generation, the knowledge of how to build them was gone, Later Chinese historians found only fragments of the story, and some dismissed those fragments as exaggeration. A fleet so capable it read like myth to the generation that came after it. The parallel is not exact. The politics were different, the reasons were different, the century was different, but the shape underneath is the one this whole story keeps returning to. An extraordinary reach outward, a deliberate decision to stop, then the slow disappearance of the capability to try again, not all at once, but generation by generation, until no one alive remembers how it was done. Stopping was never the end of the story in either case. It only felt that way at the time. The Europeans who sailed after Zheng He had none of what China had already learned. They relearned ocean navigation from nothing, at enormous cost, with enormous loss of life, because the knowledge that could have shortened that education had been burned before they ever set out. We are, in some sense, relearning how to go to the moon. Not from nothing, too much survived for that, but rebuilding capability that already existed once, at a cost decades of continuous development would never have required. And the world did not wait either time. After China withdrew, Portugal worked down the African coast, Spain crossed the Atlantic, and 2 centuries later, European ships arrived in Chinese waters carrying a balance of power China had never had reason to prepare for. After the United States stopped at Apollo, the Soviets kept flying for a while. Then China began its own program almost from nothing, and Europe, Japan, and India built capabilities that did not exist when Cernan climbed that ladder. China now approaches the moon with hardware and ambition the United States never had to plan around in 1972. Whichever country plants a lasting foothold at the South Pole first does not just win a flag on the ground. It controls the ice, builds the infrastructure, and writes the norms everyone after it has to live inside. That may decide more of this century's balance of power than anyone currently expects. That is the civilizational scale of it. The human scale is smaller and harder to look at directly. For the people who built Apollo, this was never only a job. It absorbed everything. Engineers worked extraordinary hours by choice, not obligation, because the goal was specific, the deadline was real, and the stakes were understood by everyone in the building. That combination built a community with a shared identity unlike anything before or since inside American engineering. George Mueller ran NASA's human spaceflight program through Apollo. Decades later, he called shutting down the Saturn V production line the worst decision in the history of the American space program. He had understood at the time exactly what it would cost, and he fought against it, and he lost. The engineers ordered to dismantle the line called it a kind of mourning, not for a person, but for something they had spent years building that could not easily be built again. Rocco Petrone, who ran Apollo's operations at Kennedy Space Center, said later that when the final Saturn V rolled out and the line went dark, he felt something irreplaceable leave with it. Not just hardware. The knowledge, the culture, the particular community of people who knew how to do something no one had ever done before. That is why the knowledge disappeared as fast as it did. Not incomplete paperwork. People. Once they scattered, reassembling that community 50 years later meant relearning through experience what had originally been learned through experience. Slowly and expensively, one mistake at a time. That is a real part of why Orion and SLS took so much longer and cost so much more than Apollo ever did. With computers and materials Apollo's own engineers could not have imagined. 12 men made that walk. Not one of them came home unchanged in an ordinary way. Standing on the moon means standing on another world with Earth hanging in a black sky. 4 times the size the moon looks from Earth, blue and white and unmistakably fragile. Over ground no wind or rain has touched in billions of years. in a silence broken only by your own breathing inside a suit. What the 12 came back describing was not pride. It was perspective, a sudden and lasting sense of how small human quarrels look from outside, and how precious the earth looks from a place with none of it. Edgar Mitchell called his moment an epiphany, an overwhelming sense that everything was connected, and spent the rest of his life studying that feeling seriously enough to found an institute for it. Buzz Aldrin came home to depression and alcoholism, and said plainly years later that nothing after the moon ever matched it. James Irwin came back with a faith he had not carried up the ladder and gave the rest of his life to it, describing the moon as the place he had felt God most directly. Alan Bean became a painter, devoting his career to Apollo scenes and mixed actual lunar dust into his pigments, so the moon itself was part of every canvas. Charlie Duke's marriage nearly did not survive what he brought home until he found his own way through it years later, through faith as well. These are not stories about men who accomplished something remarkable and then moved on comfortably. They are stories about people who had an experience so far outside the ordinary range of human life that they spent the rest of it trying to understand what had happened to them, to integrate it, to make it mean something they could live inside. 12 people have had that experience. In the 50 years since, no one else has. That is a kind of poverty no budget chart or contracting analysis captures, a poverty chosen through a long chain of ordinary political decisions to keep the experience sealed inside 12 people who are now in their 80s and 90s. Jack Schmitt is one of them, the only trained geologist to ever walk on the moon. He has spent the decades since arguing for return, testifying, writing, lecturing, growing frustrated in public at how long the argument has taken. He understands, better than almost anyone alive, exactly what was left unfinished, and exactly what it has cost to leave it that way. He is in his 80s now. The clock on that particular kind of understanding is not an abstraction. It is running. Schmidt's clock is a human one, measured in decades left to a man in his 80s. Step back far enough, and the clock changes entirely. Apollo happened because 5 things lined up at once. A specific goal, a hard deadline, stakes that felt like national survival, money on a wartime scale, and an institution still young enough that it had not yet calcified into habit. After 1972, none of those 5 conditions were ever present together again. The stakes shrank the moment the Soviets conceded the race. The money shrank with the stakes. The institution matured into caution, and the goal, once achieved, had nothing left to replace it. The Roman pantheon has stood for roughly 2,000 years. It does not need to be re-poured, re-quarried, or re-argued for every few years. Stone, once set, holds itself up. A space program is not stone. It holds itself up only through continuous reinvestment in people, in facilities, in the specific knowledge of how to build the next rocket. And the moment that reinvestment stops, the capability does not wait patiently in storage. It erodes. NASA did not collapse after Apollo. It kept doing serious science. It kept a foothold in low Earth orbit for decade after decade. But the specific capability to send a human being beyond that orbit was allowed to lapse, and what has been rebuilt to replace it costs more and does less than what already existed in 1972. Not a monument. A muscle. And muscles that stop being used get weaker, not preserved. Consider what the other timeline might have looked like. If the funding line from Apollo had simply continued, the lunar base planned in 1969 breaks ground in the late 1970s, on a sunlit ridge near the South Pole. By 1985, it holds a rotating crew of 6 to 12 researchers on 6-month tours, drinking water pulled from confirmed polar ice. By 1990, the crew has grown past 20, hundreds of kilograms of new samples have come home, and a radio telescope on the moon's far side is listening to a sky Earth's own noise, has always drowned out. By 2000, the base is producing its own propellant at scale, staging missions out toward nearby asteroids. By 2010, a crewed mission leaves for Mars, its tanks topped off in lunar orbit, with fuel that never had to be launched from Earth. By 2025, in this version of events, there are people living on both worlds. That timeline is speculation. Real programs hit real setbacks the tidy version leaves out. But the direction is not speculation. 50 years of continuous investment would have produced a fundamentally different level of capability. And the moon would be a place we operate, not a place we are preparing to visit again for the first time. The moon itself has been wading through all of it. It is roughly 4.5 billion years old, formed when a Mars-sized body, one astronomers now call Theia, struck the young Earth with force equal to trillions of nuclear weapons, an impact violent enough to melt significant portions of both worlds. The moon's gravity holds Earth's axial tilt steady. Without it, the tilt would wander chaotically over millions of years, and the climate swings that would follow are severe enough that whether complex life could have survived them at all is an open question. The moon's pull has also been dragging on Earth's rotation for the entire 4.5 billion years. When the moon first formed, a day on Earth lasted about 6 hours, and tidal friction has stretched that day out to the 24 we now take for granted, while the moon itself drifts a few centimeters farther away every year. Roughly the length your fingernail grows in that same stretch of time. It has stirred the oceans too, and some researchers think the tidal pools it created, filled and emptied twice a day, may have been where the first self-copying chemistry ever concentrated enough to become life. Not a rock beside us, a collaborator in everything Earth became. 6 Apollo landings gathered the first fragments of that story. Understanding the rest of it will take decades, maybe centuries, of returning with better instruments. And beyond the science, the moon may hold what expansion past Earth actually requires: water and helium-3 buried in the regolith that fusion research has long eyed as fuel, a vacuum useful for manufacturing nothing on Earth can match, and polar sunlight nearly constant enough to run on. It has been sitting there for 4.5 billion years, waiting for the intelligence that evolved next door to come understand it, and eventually to use it as the first step toward everywhere else. Here is where things actually stand, stripped of both the optimism and the dread. Artemis 2 is meant to carry 4 astronauts around the moon in 2025 or 2026, the first humans past Earth orbit since Cernan's crew. Artemis 3 will attempt a landing near the South Pole using a Starship lander that has not yet flown a crew or touched lunar ground, paired with an Orion capsule carrying the same cost structure examined earlier in this story. If it lands, the crew will spend a few days on the surface before coming home. Beyond that sits the Lunar Gateway, a small station built with European, Japanese, and Canadian partners, and beyond that, proposed once again, an actual base, this time near the rim of Shackleton Crater, where sunlight and shadowed ice sit close enough together to make a real settlement possible. Whether any of it gets built depends on budgets not yet approved, milestones not yet flown, and political will across administrations that has never once, since 1972, survived that long. The direction is better than at any point in 50 years. The South Pole has replaced Apollo's safe equatorial plains as the actual target. The commercial partners are more capable than they were 5 years ago. The coalition is wider than a single Cold War rivalry ever was. None of that guarantees anything. It only means the odds, for the first time since Cernan's ladder, are not obviously against us. And there is a cost underneath all of it that no budget chart has ever captured. Every person alive today was born after the last human being left the moon. No one now living has stood on another world. What is left of that experience survives only in the memories of a dozen men, most now in their 80s and 90s. And when it survives only in memory, it does not pass to the next generation the way a skill passes from a hand that is still working. It passes as a story, told across a gap no contemporary conversation can close. That is what the 50 years actually cost, not just missions, not just knowledge, but the living chain of people who could say what it is like and hand that understanding forward directly. Jack Schmitt still carries his end of that chain. He is the only trained geologist who ever walked on the moon, and he has spent 50 years testifying, writing, and arguing for exactly the water ice under those permanently shadowed craters that current plans now depend on. He is in his 80s. Whether he lives to see someone else make that walk is not something anyone can promise him. On December 14, 1972, Eugene Cernan climbed the ladder of his lunar module for the last time and said the words he had prepared. "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." Then the hatch closed, the engine fired, and the moon has stayed exactly as he left it ever since. The footprints are still there, pressed into powder that no wind has ever disturbed. The flags are almost certainly bleached white by 5 decades of raw sunlight, and the retro reflectors Apollo left behind are still doing their job, right now, bouncing laser light back to Earth, precise enough to measure the distance between the two worlds down to a few millimeters, the one piece of that whole program still actively at work. Look at the object itself, plainly. A sphere of rock, 3,074 kilometers across, a little under a third the width of Earth, sitting at 384,400 kilometers away, close enough that light crosses the gap in about a second and a quarter. Its oldest rocks are older than complex life on the world beside it. 6 landing sites and 12 sets of footprints sit on its near side, undisturbed, and with no wind or rain to ever touch them. They will outlast every building and every government and every civilization now standing. Still readable a million years from now, maybe 10 million, the most durable thing our species has ever made. The footprints prove something simple. We did it once. The 50 years since prove something just as simple and harder to sit with. Once is not enough. Whether we stay this time is not a question written in the stars or decided by physics. It is a question being decided right now in budget votes and launch tests and treaties still being drafted by specific people who will either choose to keep going or choose again to stop. Nothing about the outcome is guaranteed. What is guaranteed is only this: the footprints are still there, the reflectors still answer, and the question is still ours. The moon will wait. It has always waited.